In this presentation, I would like to talk to you about the field surveys we did of the 2019 Krakatau tsunami, or 2018 Sunda Strait tsunami. My name is Miguel Esteban, and I'm a professor of the Department of Civil and Environmental Engineering at Waseda University in Tokyo, Japan. First of all, I'd like to acknowledge that this work is a large collaboration between many universities, and thus there are many co-authors in this presentation work. So some of these co-authors come from Indonesia, Bandung Institute of Technology or Institute Teknologi Sumatera. There are also other colleagues in Japan, in Waseda University, Niigata, Tokyo City University, and there is also one collaborator from Liverpool, John Moores University. This is the outline of the presentation. First, I'll start by giving you some background on the Sunda Strait, the 1883 Krakatau eruption, the 2018 tsunami. Then I'll talk about methodology, the run-up and inundation surveys, questionnaire surveys, bathymetry surveys, the aerial drones that we used. Then I will go and talk about the results, the run-up surveys, bathymetry, and tsunami awareness and evacuation behavior of survivors. And finally, I'll give some conclusions. The location of the Sunda Strait, well, the Sunda Strait is located between the islands of Sumatra here and Java here, where the capital is. If you see here, this is a close a zoom in of the area, and it indicates that this is the southern shoreline of Sumatra. This is the western side of Java, and the Krakatau group of islands is here in the middle. They're composed of 4 islands. 3 of these are the remnants of the island that existed before 1883. These 3, and this one in the center came out of the water in 1927. So originally, in 1883, there was this big volcano called Krakatau. It exploded, and as a result of that, over 75% of the island disappeared. This explosion is very famous in volcanology. It could be heard about 3,000 miles away in New Zealand, and it generated a tsunami with waves up to 40 meters high that went on to kill in excess of 36,000 people. In 2018, there was another eruption, this time from Anak Krakatau. So Anak Krakatau is this island that came out from the sea in the 1920s. And literally this means the son of Krakatau. So, and as a result of this 2018 eruption, then part of the island collapsed into the sea, generating a tsunami that went on to kill over 400 people. The methodology that we used, we conducted 2 field surveys, one on the 13th to 17th of January 2019, i.e. the month after the eruption took place. We surveyed inundation heights and run-ups around Java and Sumatra. We recorded tsunami damage mechanisms, and we also conducted questionnaire surveys of survivors. And here you can see one of the co-authors interviewing survivors of the tsunami and asking them what they knew about tsunamis, when and how did they evacuate, to where did they evacuate, etc. In total, we had 104 respondents, and the questionnaire said they had 34 questions. Then, several months later, in the 15th to 18th of August 2019, we conducted a second survey of the actual islands of the Krakatau archipelago. We couldn't do this in January because it was very dangerous. The Indonesian authorities wouldn't let us, so we had to come back in August and survey the run-ups along the sides of the mountains. Here you can see one of our teams surveying the run-up on Setung Island, which is close to Anak Krakatau. So Anak Krakatau can be seen here, and the actual tsunami overtopped this island. So in this case, we could only find out, in some cases, the run-up. In some cases, we just measured the maximum height of the island. Here you can see how the vegetation is still damaged. We also conducted bathymetry surveys using Garmin echo sounders, using two boats, the main boat that we used to move around, and a second smaller boat that could be used on shallower water. We used also a Phantom 4 drone to obtain digital elevation maps of Anak Krakatau, and we also did key informant interviews with guards of the national park of which Krakatau is part of. Some of the results. The tsunami run-ups around Anak Krakatau were in the order of 40 meters in Setung, as I explained before. So this island was overtopped, so this was the maximum we could measure. In another one of the islands, Panjang, the run-ups were in excess of 80 meters, and finally around Rakata, they were in excess of 45 meters. Note that because this is the island that collapsed, these three islands offered some shielding to the coastlines of Java and Sumatra. We also conducted bathymetry surveys. This video shows me in the small boat going around the island measuring the bathymetry, but we not only did the bathymetry around the main island, but we also did many of the lines. So all these blue lines show the bathymetry that we collected. And this bathymetry is very complex. As a result of the 1883 eruption, it suddenly has a lot of dips. It goes from shallow to very deep very quickly and shallow again. We will make all the bathymetry publish. We will publish all the bathymetry with one of the papers that we have currently accepted in the next few months. So anybody who wants to use it for numerical simulations can do so. Using the digital elevation model, we could capture what Anak Krakatau currently looks like and obtain a map for it, as you can see here. Now, using three different sets of data, we could see that this is the original cross-sectional profile of Anak Krakatau, and this is the one that we measured. So if you want, all this area was destroyed as a consequence of the eruption and collapsed onto the sea. We estimated this volume to be 0.2 to 0.5 cubic kilometers. In their simulations in 2019, Greeley and et al. Estimated this to be lower, and this could be the reason why the simulations of Greeley et al. Appear to underestimate to some extent the run-ups caused by the flank collapse of Anak Krakatau. We also conducted these surveys around Sumatra and Java Islands. Overall, we found that the run-up heights and inundation heights were relatively modest. The maximum we found was in Sipenyu Beach, where we recorded inundations of around 10 meters and run-ups of 12.5 meters. And that's this area around here. Most other areas, the inundation heights were relatively low, in some cases less than 1 meter. And this explains why the number of casualties was not as high as in other tsunamis. Note also that there are no major cities or towns in most of these areas, and this could be maybe a consequence of the 1883 event that maybe devastated the area and hasn't recovered to some extent still. We also conducted questionnaire surveys. We asked people if they knew what tsunamis were. 96% of respondents said they did know what a tsunami was, and we asked them if they knew whether they could evacuate, though only 23% of people said they knew how to evacuate in the event of a tsunami. No respondents indicated that they had received an evacuation order before the arrival of the tsunami. After the arrival of the tsunami, evacuation orders were given by some sort of authority figure, and 68% of people followed these. When asked what did they do after receiving this evacuation order, 92% of people responded that they prepared to evacuate, and only 3% of people that they waited, that they collected information, and 30% of people said that they contacted family members. Note that the area does have some evacuation buildings, as shown in this video here, and thus in places like Lantera, when people were given an evacuation order, they did proceed to this evacuation building. This means that people generally appear to know what to do to some extent, but because there's no early warning system, and the few elements of a warning system that did exist were in a state of disrepair, although they were directed against offshore tsunamis, not something coming from Anak Krakatau. Now the conclusions. The flank collapse of Anak Krakatau generated tsunami that had run-up heights of in excess of 80 meters in the islands around the volcano. In areas of Java Island, we measured inundation heights of around 10 meters, but mostly these were 4 or 5 meters elsewhere around in the Sunda Strait, or even in many cases less than 1 or 2 meters. The estimated volume of material that was lost during the eruption was 0.2 to 0.5 cubic kilometers. The islands of the Krakatau archipelago provided some shielding to the areas of Sunda Strait around them, although it is worth noting that the complex bathymetry might have also provided some reduction in tsunami wave energy. Awareness of tsunamis is relatively high through warning systems were non-existent, and better evacuation systems are also needed in the area. Now, as a result of these field surveys, we've published one paper already, and another paper has been accepted and will be online in the next few months. In this paper, as an appendix, we've published the bathymetry data for anybody that wants to use it. And that's all. If you have any questions, please contact me at the email shown here, or ask thank you for your attention.